Hello everyone, I am Jim Sesanga. Today, I'll be walking you through my summary of machine learning with Python. We'll cover 6 modules from core machine learning concepts all the way to dimensionality reduction in about 15 minutes. Let's get into it. This course runs across 6 modules: machine learning fundamentals, k-nearest neighbors, decision trees, ensemble learning, support vector machines and k-means, and finally, PCA. Each module builds on the last, so by the time you finished, you have a complete picture of the most important supervised and unsupervised machine learning algorithms. These are the ones that I use today. So let's go through the machine learning fundamentals. Machine learning is the field that gives computers the ability to learn without being programmed. Instead of writing rules, we basically let the data teach the module. There are 2 types: supervised and unsupervised learning, where in supervised data is labeled, and in unsupervised, the model finds patterns on its own. Models themselves are either deterministic, where there are exact relationships and no randomness, or they can be probabilistic, which adds a random error components to make them more realistic. Linear regression is the most fundamental example. It models the relationship between variables as a straight line, and we find that line using the least squares method, minimizing the gap between predicted and actual values. The process of linear regression is through 4 steps. 1. You hypothesize the deterministic components. Then you specify a probability distribution of random error. Then, thirdly, we evaluate the fitted model. And finally, you use the model for prediction and estimation. Moving on to module 2, the k-nearest neighbors. This algorithm is as intuitive as they get. To classify a new point, find its k closest neighbors in the training data and take a majority vote. So we have 3 steps. First, we calculate the distances. Here you compute the distance between the test points and all training data. Then we sort the neighbors. We sort all pairwise distances to find nearest k-neighbors. And finally, you take a majority vote. You classify the point based on the most common class among k. We use Euclidean distance when features measure similar things, and Manhattan when they don't. And if features are on different scales, normalize them first. Otherwise, larger scale features will dominate. The golden rule is that never tune K using test data. Test data simulates real world. Using it for tuning breaks that simulation entirely. KNN requires no training phase and makes no assumptions about data distribution. The downside is speed. Every prediction scans the entire training set, which becomes expensive fast. Moving on to module 3, Decision trees. Decision trees split data repeatedly based on feature values, trying to create groups that are as pure as possible. Purity is measured by Gini impurity, which ranges from 0 to 0.5, or it is measured by entropy, which ranges from 0 to 1. Gini impurity is faster, though entropy is slightly more thorough, but both lead to similar results when they are used in practice. Now, the biggest danger is overfitting. You see, when a tree grows too deep, it memorizes noise. So we have to fight this with pruning. Pre-pruning limits growth during training. There are parameters like max depth, and then just pruning grows the full tree first, then trims it. This is actually preferable because a useful splits can sometimes follow what looks like poor one early on. Decision trees are highly in, sorry, decision trees are highly interpretable and need minimal preprocessing and handle non-linear patterns naturally, but they are sensitive to noisy data and can vary wildly. Like they can vary, how should I say it, angrily, maybe, with when there are small changes made to the training sets. Moving on to module 4, Ensemble learning. This combines many weak modules into one strong one, or a supermodel. The foundation is bootstrapping, which is repeatedly sampling your data with replacements to create many different training sets. Bugging trains multiple models in parallel. Those bootstrapped sets and averages their predictions. It reduces variance and overfitting. Random forest is bugging with an extra twist. At each split, only a random subset of features is considered. This decorrelates the trees and makes Ensemble far, far more powerful. It's robust to outliers, handles nonlinear data well, and is one of the most reliable algorithms available. Boosting is different. It's sequential. Each model focuses on the mistakes of the previous one, iteratively reducing bias. Bugging is parallel, boosting is sequential. That distinction is worth remembering. Moving on to module 4, the random forest. We talked about the random forest previously, and we said that it is just bugging with an extra twist. And we said that bugging is parallel. Now, going into the random forest, what is the random forest? How does it work? So, the random forest basically for every tree, subsample. The first thing you do is to subsample examples with replacement, which is bootstrapping. Then you randomly pick features at each split. Then you build the tree on random features only. And finally, you average all the trees for final prediction. That is basically how the random forest works. Because it is robust to outliers, it works well with non-linear data, and it lowers the risk of overfitting, and finally runs efficiently on large datasets. And its disadvantages: it is biased with categorical variables, it has a slow training time, it is not suitable for linear or sparse data, and it has greedy splits, which are not globally optimal. On to module 5, we shall go to support vector mechanics. SVM finds the hyperplane that best separates classes by maximizing the margin between them. A wider margin means better generalization. SVMs can also detect and ignore outliers, which makes them naturally robust. The kernel function is what makes SVM truly powerful. It maps data into a higher dimensional space where it becomes linearly separable without the computational cost of actually doing that transformation. Cheap mathematically, extremely powerful in practice. Gamma controls the influence radius of each training point. Low gamma gives smoother, broader boundaries, and yet high gamma makes boundaries tighter, but risks overfitting. Getting gamma right is one of the main tuning challenges. On to k-means clustering. K-means is our first unsupervised algorithm. No labels, we're just finding natural groupings instead. The algorithm assigns points to k clusters, minimizing distance to each cluster's center. Then it iterates until the clusters stabilize. It's simple, fast, and the most popular clustering algorithm out there. Its limitations are that it only works when the mean is defined, it's sensitive to outliers and to the initial random seed, and it struggles with non-spherical clusters. When k-means works, it works brilliantly. Just now when it wants, it will not. And going on to the principal component analysis, or module 6, also short is PCA. PCA reduces the number of features in your data while preserving as much information as possible. It finds the directions of maximum variance, called principal components, and projects your data onto them. Its lossy compression, discarding lower variance components permanently, loses some information. That's why it's lossy. So that's the trade-off. It's smaller, faster data at some cost of detail. There are two important rules. PCA assumes linear correlations, so it won't capture nonlinear structures. And feature scaling before PCA is critical. Always document the scaling that you use. Main applications of PCA are for image compression, preprocessing for other ML tasks, facial recognition, and data visualization. Moving on to the algorithm comparisons, we're going to compare these algorithms. Here is the full comparison. The key question for each algorithm isn't just what it does, it's when to use it. Regression is for numbers, KNN, and decision trees. when interpretability matters. Random forest for accuracy on complex data, SVM for high dimensions, k-means for discovering clusters, PCA as a preprocessing step. Keep this table in mind and you'll always have a starting point. The key takeaways, the 7 things you need to remember. First, match your algorithm to your data type. Second, never tune on test data. Third, ensemble methods almost outperform single models. Fourthly, processing is not optional. Normalize balance, scale as needed. Every model involves trade-offs. That's one thing you should keep in mind. PCA is essential for high dimensional data. And finally, always use cross-validation to guard against overfitting. These 7 principles will serve you well beyond this course. Moving on to the Idris dataset. The Idris dataset was our sandbox for the course. 150 samples, 4 features, 3 classes. It's clean, small, and perfect for learning because it lets you focus on understanding the algorithm rather than fighting with messy data. Nearly every algorithm we covered was demonstrated on Idris. Now, model selection. How to select the right model. When choosing your model, start here. Is your data labeled? If yes, are you predicting a number or a class? Then ask how important interpretability and speed are. If no labels, are you grouping or reducing dimensions? This flowchart won't always give you that final answer, but it gives you an informed starting point every time. Moving on to overfitting. Overfitting means your model is too simple. It misses real patterns. Overfitting means it's too complex. It memorizes noise and fails on new data. The goal is always the middle ground: pruning, regularization, bugging, and more data. Are your tools for getting there? This trade-off never goes away. Every machine learning project involves managing it. Now we move on to the real world applications. In actuality, machine learning is everywhere. KNN is in finance and agriculture, dimension trees in healthcare, random forests in stock prediction, SVM in image recognition, means in customer segmentation, PCA in facial recognition. The algorithms we learned aren't just academic, they're running in production systems right now as we speak. As I speak, right? Yeah. Okay. So these are the Python tools you should have for machine learning. Everything covered in this course lives in 4 Python libraries. Scikit-learn, I always get it wrong. Scikit-learn for the algorithms, NumPy for the math, Pandas for data handling, and Matplotlib and Seaborn visualization. Once you master these 4, you have everything you need to build and evaluate real machine learning models. What we learned. So, today we've learned about the 6 modules and the 8 algorithms, 1 Python toolkit. The foundations are solid. What you do with them from here is up to you. Thank you very much. I hope this was useful. Take this course, grab your certificates. Good luck. Yours, Jim Sesanga.